So Tut's method tells you how to lay out the nodes of a planar graph in a plane so that the edges don't cross. If you don't have a planar graph, if you have an arbitrary graph, you need to use more sophisticated methods to lay out a graph so that it can be easily visualized. So as we saw in the last set of slides, Tut's method for laying out a planar graph places each node at a position that's the average of its neighboring nodes. And so each of the nodes is applying a force to the current node's position. And so that's an example of a force-directed layout, and there's quite a few different force-directed layouts. A popular one is called GEM, and that's what was used to lay out this example. This is a interaction graph between yeast proteins. There's about 1,500 yeast proteins and about 2,000 interactions, and so the yeast proteins are indicated by nodes and the interactions are indicated by edges. So in the GEM algorithm for force-directed layout, we're simulating the force of a spring system. So each edge between two nodes corresponds to a spring, and that spring has a rest length. If the nodes are farther than that rest length, then they'll be attracted to each other. If they're closer than that rest length, then they'll be repelling each other. And also, if you have high degree nodes, if you have a node with a lot of neighbors, then GEM will make that rest length of the springs larger to try to push away those neighbors, since there's so many of those neighbors sharing an edge with that high degree node. There's also a repulsion between nodes even if they're not connected by a spring, so that nodes don't end up on top of each other even if they're not connected by an edge. And that repulsion force is basically equal to 1 over the distance between any two nodes. And then finally, all the nodes experience a force of gravity towards the center of the graph to keep things from wandering too far away, and a small random perturbation force just to make sure that nodes take unique positions. As we talk about the layout of graphs by placing nodes, it's good to think of the centrality of nodes. And centralities are ways of analyzing where a node should be positioned in a layout. Should it be more central or should it be on the periphery here? And so these nodes that are blue in color are central nodes, and these nodes that are red in color are non-central nodes. And there's many different centrality metrics, ways of measuring how central a node should be in a layout. Node degree is a simple method where you just count the number of edges that a node has, and so nodes with high degree should be placed towards the center, and nodes with low degree might appear on the boundary. PageRank is a kind of centrality measure which Google uses to find popular web pages by basically counting the number of incoming links from other web pages. Another is based on the isolation metric. You can think of the distance between nodes. For example, this green node here to this red node has 3 edges between it, so its distance would be 3. It's the length of the shortest number of edges to get from one node to another node is the distance. The isolation metric basically adds up the distance from a given node to all the other nodes in the graph. And if I add those up, then I'll get a smaller result for nodes towards the center of this graph and a larger result to nodes in the periphery of this graph in this particular layout. And so you can think of closeness centrality as basically the inverse of that isolation metric, so that nodes with high closeness centrality would have low isolation metric. You can also think of graph centrality, which is like the isolation metric, except I'm not taking the distance to all the nodes and adding them up. I'm taking the distance between a node and the farthest node away from it. And 1 over that gives me what's called the graph centrality. And finally, there's betweenness centrality. Betweenness centrality basically looks at every node, every pair of nodes, and finds the shortest path between that pair of nodes. If I take the shortest paths between any node and any other node, all of those shortest paths, how many of those shortest paths go through a given node? That tells me the betweenness centrality of that node. And so if I take every shortest path between every node and every other node, those shortest paths will likely go through these central nodes more than they will go through these peripheral nodes. And so that's what we have plotted here. nodes plotted based on their betweenness centrality. How many of the shortest paths between any two nodes go through each of these nodes. It's high for these nodes that are blue in color and low for these nodes that are red in color. And you can also compute that for an edge. How many shortest paths go through an edge? So we can use that betweenness centrality or any of these centrality metrics to simplify a graph. And so, for example, if I compute the betweenness centrality of edges of my network of yeast proteins, edges that have low betweenness centrality have few shortest paths going through them, and edges with high betweenness centrality have a lot of edges going through them, and so a lot of shortest paths going through them. And so if I remove edges that have few shortest paths going through them, you might think the impact would be less than if I have a lot of shortest paths going through that edge. And so I've plotted the betweenness centrality of edges here, and I've basically removed the lowest betweenness centrality, the ones that are very dark blue, and left the highest betweenness centrality edges, the ones that are in red here. And I've not removed any edge if it creates a disconnected graph. So the result is a graph that has as many edges as it has nodes, about 1,500 edges and 1,500 nodes. So I get something like a tree that's minimally connected, but I've retained the high betweenness centrality edges and removed the lowest betweenness centrality edges. And so what's left is kind of the communications backbone, the most often used edges when I'm finding the shortest path between any two nodes, and that simplifies the layout. Now I've got fewer edges in order to compute spring distances when I use the same GEM layout, force-directed layout for this graph on the right than I'm using for this graph on the left. The nodes spread out more because I've got fewer springs, and the nodes are freer to move around into unique places. And you can visually see the relationship between nodes better in this layout than in this layout. You're also looking at fewer edges, so you can always add back in the edges as necessary to add back in those low betweenness centrality edges to see a more complete view of this graph, but the nodes would still be positioned better than they are when you try to compute the layout using all of those edges. So there's other techniques for laying out graphs. Here's an example technique called edge bundles, where we just put all of the nodes in a ring. We make a circle, a radial layout of nodes, and then we draw the edges in the region inside this disk surrounded by this circle of nodes. And we can start to group edges together. If we have some way of measuring the similarity of edges, we can create basically wire bundles called edge bundles that simplify the visualization of this graph. In this case, these are emails that were part of the litigation for a company called Enron between 132 employees back in 2001. And here's a couple different layouts. This is a force-directed layout of these node positions, and then we've, instead of having the edges just go straight line connecting each node, we've tried to bundle the edges together so you can kind of see main communication pathways in these representations. So how do you find two edges to be similar or not similar to each other so that you can bundle them? Well, this for that task, it's useful to form communities to try to cluster nodes together in communities that are sharing similar edge behaviors, similar edge connections. And so in order to find communities, we can remove edges in order of decreasing centrality or decreasing betweenness centrality, which is what we used. So instead of removing the low centrality edges like we did for node layout before, now we're removing high centrality edges. And so now we're removing the edges that are part of the main communication pathways. And what that does is that disconnects a graph, and it isolates nodes, and it isolates nodes in clumps, and those clumps form clusters that form communities. And so you can think of a community of nodes communicating through another community of node across a high between a centrality edge. And so by removing our edges from the highest between the centrality to the lowest centrality edges, we're creating a hierarchy of these communities. As we remove those edges, we can create nodes that represent where those edges connected communities to, and so we can use the resulting communities to figure out the order in which to lay out vertices on the periphery on this circle. And then by merging those clumps together, we can place vertices in the interior to denote higher level communities. These are called community nodes. They're not part of the original graph. They're just used to represent communities, to represent mergings of clumps of nodes. And so here's some examples of edge bundle communities. In this case, we took every football game between colleges in the United States. The University of Illinois is one of these colleges. And by just taking anytime any college played another college, we would connect that with an edge. And by looking at the final graph, removing the high between the centrality edges, they started to isolate communities, and we were able to figure out a layout that represented these low-level communities. We basically rediscovered the conferences. And so just by looking at all the games of football played between one university and another in the U.S., we were able to discover the conferences that organized the games between colleges in the U.S. And then we can use that community structure to figure out an edge metric. So edges from one section of the community to another section of a community can then be clumped together and form these edge bundles by basically attracting them to these edge node positions. So here's an example of the actual communities from Enron, and here's the communities we discovered. These don't lie in the same position as the rest of these. For example, here's where the president of Enron is, and he's listed here in the CEO section here. But we found the same actual communities were discovered by basically removing high between the centrality edges from the graph of all emails from one employee to another. Ended up revealing these communities. And as we'll see later, it's useful to be able to filter out and look at details interactively in these edge bundle examples or in any large data set. So we can click, for example, on the CEO of Enron, Kenneth Lay, and see all the email that was sent in this data set to all the other employees, to all the other communities. For example, I can click on Illinois and I can see all the other Big Ten conference games that it had, but I can also see the games it had to other places outside of its conference. So there's a variety of methods that we've just seen to visualize graphs, not necessarily planar graphs, but any graph, social networks and other graphs, and they're based largely on analyses that are enabled by that centrality, the definition of some kind of centrality of the nodes.